OK, alors on va commencer maintenant le colloquium. Ça me fait très plaisir d'introduire Samit Dasgupta de Duke University, qui va parler de Stark's Conjectures and Hilbert's 12th problem. So Samit hardly needs any introduction. He's been a frequent visitor to Montreal already as a graduate student and as a postdoc, and he's made many visits ever since. And today we're very happy to host him at this colloquium. Samit.
All right, well, thanks. It's very nice to be back in one of my favorite places to visit. I'm going to speak today on two central problems in number theory and how they're related. So, let's see, this is not working. All right. So, so the two questions I want to talk about. The first is the question of explicit class field theory. So for those who are fond of the Langlands program, this can be viewed as the simplest case of the Langlands program, the GL1 case, which from the Langlands perspective is completely solved via class field theory. But you can ask for a refinement, which is to make that explicit. And this generalizes classical results in complex multiplication. And it's been sort of made famous by sort of a very particular question in this direction asked by David Hilbert in his famed ICM address of 1900 in the 12th in his famous list of 23 problems. And the second theme that's also a very prominent one in modern number theory is that of special values of L functions. So there's lots of conjectures about the special values of L functions. Probably the most famous one is the Birch-Swinnerton-Dyer conjecture, which talks about the value of the L function of elliptic curve at s equals 1. But there's somehow a GL1 version, a version for Ray class characters that's still open, known as Stark's conjectures, and that's what I'll be talking about today. But these conjectures have been generalized to very broad settings for arbitrary motives. These generalizations are due to Bailenson and then integral refinements due to Bloch and Kato. And these conjectures of Bailenson and Bloch-Kato serve as some of the most motivating central problems in modern number theory. And I want to talk about each of these problems and their connections. So since this is a colloquium, I'm going to start from the foundations. So a number is called algebraic if it is the root of a non-zero polynomial with rational coefficients, such as the square root of 2 or I, or the cube root of 2. And the set of all algebraic numbers forms a field, which we denote by Q bar. So one of very natural question to ask ever since Galois laid out Galois theory, the theory of automorphisms of fields, is to describe the group of all automorphisms of this field, Q bar. There's a huge profinite group, and we don't really understand much about it. For example, we don't even understand which finite groups can appear as quotients of this group. It's sort of an open conjecture that all of them do. The Langlands program takes a modern perspective of representation theory, saying the way to understand a group is not to understand the group, but to understand all its representations. So you want to understand all the n-dimensional representations of this group. And the n equals 1 case is what was known as a class field theory. So I'll talk about that in a moment. And more generally, you can replace Q here by a finite extension of Q. Say Q joined the square root of 2. You call that F, and you want to know all the automorphisms of Q bar over F. That is, all the automorphisms of Q bar that fix F. So this will be a subgroup of the group that I called GQ. Okay. So, right, the first case, if you have a question for every n, is to understand n equals 1. So we want to understand the one-dimensional representations of this group GF, or arbitrary field F. And that's equivalent to understanding the abelianization, right? So one-dimensional representation of a group is a character. It's a homomorphism from the group into the multiplicative group of some field, which is abelian. So your representation has to factor through the abelianization. So really you're asking, what is the abelianization? That abelianization is the group of automorphisms of what we call the maximal abelian extension of your field. So let me give an example. So the field QAB, the maximal abelian extension of Q, is obtained by adjoining the roots of unity for all positive integers to your ground field Q. And this is known as the Kronecker-Weber theorem. This is sort of a classical result, a very famous result, which is, it's sort of one of the very first examples you do in Galois theory is that if you take this field of nth roots of unity, it's kind of hard to do. Okay, it's not going to work with the pointer. But if you take Q adjoint e to the 2 pi I over n, then that field is has an automorphism group over Q that's isomorphic to Z mod NZ star. That is the group of units in the ring Z mod NZ, which is an abelian group. So that's an example, and the Kronecker-Weber theorem is a converse. It says that those are basically all the examples. That if you have any field that contains Q and is Galois with abelian Galois group, then it has to be contained in one of these Q adjoin e to the 2 pi I over n's. Okay, so that's the famous Kronecker-Weber theorem. Okay, and so you might want to generalize that. So what does class field theory say? So it says if we start with an arbitrary number field f that is a finite extension of Q, and we call it f, what are all of its abelian extensions? Well, we had this indexing of the abelian extensions of Q to the e to the 2 pi I over n, Q adjoin, excuse me, e to the 2 pi I over n, and such that every field was contained in one of those. And there's a similar situation for an arbitrary field f. That is, for every positive integer n, there is a field which I'll call f sub m, which is called the narrow ray class field of conductor n. That's a lot of fancy words. But these fields satisfy the same properties that the Q adjoint e to the 2 pi I over n's do. Namely, Fn is contained in Fm if n divides m, right? An nth root of unity is contained in nth root in the field of nth root of unity if n divides m. And that the maximal abelian extension is obtained by taking the union of all of them inside of, say, Q bar. Okay. So, and the last thing that we know is that class field theory tells you the Galois groups of these extensions. So the Galois group of the field, so I won't tell you the full Galois group of Fn over F, it's a little bit complicated, but I'll tell you what the Galois group of F1 over F is. So this is called the narrow Picard group of F, or the narrow class group, where O is the ring of integers of F. So this is something I'll define in a moment. And the Galois group of Fn over F1 is some very simple quotient. It's just like Z mod NZ star. It's the ring of integers of O mod n star, and you have to mod out by some subgroup of units, which I write O star plus. So let me say this. It's easier to describe what these all are with the example. So in the case that I've done, where the ground field is Q, my field Qn is just the Q to the E, Q adjoin e to the 2 pi over n. So you take Q and you adjoin an nth root of unity. Then the Galois group of this field, as I told you earlier, is just Z mod n star. Okay, and in general, what plays the role of Z? What plays the role of Z is this ring O, which is called the ring of algebraic integers within F, which is the set of elements of F that satisfy polynomials that are not just have rational coordinates, but have integer coordinates and are monic, right? So any rational polynomial can be made integral by scaling the denominators, but the point is that you can do that and the polynomial remains monic, then you call your element an algebraic integer. And the ring of, and the set of such things forms a ring, which we denote by O. And it's a nice theorem, a nice exercise that one can prove that when your field is Q, then this set is actually just Z, which is why we call it the ring of integers in general. Okay, and then you can see, so what is this ON plus? It's the group of totally positive units within O. So in Z, the units are plus or minus 1, and the positive unit is just 1. So there's nothing there. You're modding out by just 1. So this thing on the right here is just Z mod n star. And you can prove that for Q, this narrow Picard group is just trivial. All right. So in other words, class field theory describes the automorphisms of the maximum abelian extension of F. It's just the inverse limit of the Galois groups I just described to you, the Galois groups of Fn over F. Okay, so it describes the group, but it doesn't describe the field Fab itself. So the goal of explicit class field theory is to construct the field Fab, or equivalently each of the fields Fn, because their union is Fab. And you want to do this using sort of data intrinsic only to F itself. That is, you don't want to have someone sort of tell you the answer based on knowing the answer. It has to somehow given F, spit out F ab. If you could write a computer program to take in some elements that generate F and say, from this, give me elements that generate F ab, right? That would be a nice way to say you've solved explicit class field theory, okay? And so, for example, for Q, I would say we know this because Q ab can be viewed as adjoining special values of a certain complex analytic function, the function e to the 2 pi I x. If you plug in rational arguments for x, you get e to the 2 pi I over n for all n, then you get exactly the fields that I described earlier. And their union, their compositum inside an algebraic closure of Q is exactly a Q ab. So I'd say we've solved explicit class field theory for Q using the exponential function. There's one other case where this has been done classically, which is that of quadratic imaginary fields. So by a quadratic imaginary field, I mean a field of the form Q adjoin the square root of a negative integer. And the theorem is that the field Fn in this case can be obtained explicitly via the special values of some modular functions. So these modular functions play the role of the exponential function. So Fn is, you start with F and you adjoin the J function of an elliptic curve that has complex multiplication by the ring of integers in F. And essentially you add the n torsion points to get Fn, but there's some additional sort of modular function that you apply to this, which is called the Weber function. It's a technicality that I don't want to get into. But the punchline here is that this J function and this Weber function are modular functions, okay? And so they play the role, these functions in the upper half plane play the role of the exponential function that they did for Q. Okay? So this is kind of a classical result that kind of the basic constructions of this nature were around at the time of Hilbert's writing in 1900, but it hadn't been completely, sort of written perfectly. For example, the technicalities with respect to this Weber function and stuff, this came later in the 20th century. But, by the middle of the 20th century, roughly, this was pretty much known. Okay. So as I mentioned, Hilbert codified this question of doing explicit class field theory for arbitrary fields in his ICM address. So in the 12th problem. So this is a translate, and I've kind of, taken little bits and pieces of this. And one might object that I've left out some important parts of this. So I do invite you to read the whole description of the 12th problem of Hilbert. But so the theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. And since the realm of the imaginary quadratic number field is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So as I said, they had kind of knew that this could be done already in Hilbert's time, even though it wasn't yet at that point. It was really Kronecker's Jugendtraum was to sort of finish off this case. But even Hilbert realizes already in 1900 that extending this beyond the case of quadratic imaginary is a fundamentally more difficult question. So he says that finally the extension of Kronecker's theorem to the case that in the place of the realm of rational numbers or the imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. Okay, so now I want to talk about approaches. I want to sort of link this. This is for my discussion of the first problem, explicit class field theory. And I want to kind of link this now to the question of special values of L functions. Okay, and before I get into details about this and technicalities, I want to give kind of just a historical overview. So for me, the connection between Hilbert's 12th problem and L functions owes a great deal to Stark, who stated a series of conjectures throughout the decade of the 1970s, proposing the existence of special elements in these fields, Fn, whose absolute values are related to L functions. Okay, so this gave us some hint that there should be special elements that we should be searching for when trying to generate these fields, Fn. So with respect to my talk, what's really important is the Brumer-Stark conjecture. And so for this, work of Brumer is really important. Some of this work was already done in the 60s, and Tate sort of combined the work of Brumer and Stark in his formulation of what we now call the Brumer-Stark conjecture. And that's going to play an important role later in the lecture. So going in this particular line, so there's many other directions that grew out of Stark's work, which I'm not discussing here, but following this path through the Brumer-Stark conjecture, I'll mention that Gross refined the Brumer-Stark conjecture using p-adic L functions in what is now known as the Gross-Stark conjecture. And this appeared, I think, in the same volume that Tate's paper appeared about the Brumer-Stark conjecture. I think there were consecutive articles. And then over the past several decades, really important work of many mathematicians, including Rubin, Burns, Popescu, and others I haven't mentioned here, such as Kurihara and Greither, have made the higher rank version of Stark's conjectures more precise, and not just higher rank, but even in the, so I haven't even defined what I mean by rank. So that, but even in the lower rank cases, making the conjectures very precise was done by very many mathematicians. And I'll say that very significant partial progress had been made on the Brumer-Stark conjecture by Burns, Popescu, and Greither, building on Weyl's proof of the Iwasawa main conjecture. All right, so let me talk again somewhat qualitatively about what are these Brumer-Stark and Gross-Stark conjectures about. So what is the setting that they take place in? And I'll state them precisely later. But we start with a totally real number field. So that's always the setting of these conjectures. So what is a totally real number field? That's a field that every time you embed the field into the complex numbers, it actually lands in the real numbers. So for example, Q adjoin root 2, if you embed it into the complex numbers, it will always land on the real line. There's only two embeddings. Root 2 can go to root 2, or it can go to minus root 2. And either way, the whole field will lie within the real line. That's called a totally real field. The Brumer-Stark conjecture predicts the existence of certain elements in these field extensions called Fn, when F is one of these totally real fields, that are called Brumer-Stark units. And their valuations are supposed to be related to L functions. And I know I haven't defined an L function yet. I'll do that later. But there's a very precise relationship. And so it predicts the existence of these special elements that we'd like to know exist. The Gross-Stark conjecture predicts that these units are related to p-adic L functions of F in a specific way. So that at the same time as all this was going on, the theory of p-adic L functions is being developed, building on the work of Kubota and Leopold. Deline and Rivet, along with Kasu-Nogues, established p-adic L functions for these totally real fields F. And Gross realized that the amazing fact is that these same units that are related to L functions via the Brumer-Stark conjecture stated by Tate are actually related also to p-adic L functions in a conjecture that he stated. Okay, so before I talk about the work that I want to mention today, I want to talk about some older work. So starting with my PhD thesis, a lot of the work of which was done right here in Montreal, some of it in this building. So I'm very happy to be speaking about it here. Is we stated a conjectural exact formula for Brumer-Stark units. So the first example of this was basically my PhD thesis, which I did under the supervision of Henri Darmon here at McGill and with my advisor at Berkeley, where I was officially a student under Rivet. And so we wrote this up in a paper for the case where F is a real quadratic field. And later I generalized this to arbitrary totally real fields in several works. With Pierre Charlevoix, Matthew Greenberg, and Michael Spiess. Okay, then later, together with Henri and Robert Pollack, we proved sort of the rank 1 case of the Gross-Stark conjecture. Again, I'll mention what this rank business is later. And then building on this work with Darmon Pollack, Kakde, and Ventulo and I proved the higher rank case. I mean, if you're paying very close attention, I mentioned that the Gross-Stark conjecture is about these Brumer-Stark units, which at this point we don't know exist. So it seems a little bit funny to say we proved the conjecture. Basically, we proved the part of the conjecture that you can prove without knowing the units actually exist somehow. You kind of tensor with Q's to make the units exist in a trivial way. And then once you know that they exist, then you can prove the conjecture. So it's kind of the aspect of the conjecture that you can prove without knowing the units actually exist. Okay.
So when you say the units are known to exist, I mean, we know we have Dirichlet's unit theory.
They exist rationally, and you want to know that they're actual integral units, right? So they exist. You imagine a Q vector space and a Z lattice sitting inside, and you know the element exists somewhere in this Q vector space unconditionally. And then Gross's conjecture is that that element satisfies some formula, and we prove that that element satisfies the formula it's supposed to satisfy. So it's an unconditional statement. Now the Brumer-Stark conjecture is kind of asking a different question, which is that element, which you've now proven satisfies this p-adic formula, does it actually live in the integral lattice that you want it to live in inside of this rational vector space? And that's kind of a different question. Okay, but well, so the theorems that I want to announce today. So the first theorem is that the Brumer-Stark conjecture holds as long as you invert 2. So it kind of lives in this Z lattice tensored with Z bracket 1/2. So you have to sort of allow yourself a denominator of 2. And I can say a little bit about the denominator of 2. I think I mentioned this in my talk yesterday for those of you that were there, about the power of 2 is a bounded power of 2. And I can say a little bit about what that bound is. And also I can say that the conjectural formula that I mentioned, the one that I sort of started when I was here in Montreal, for Brumer-Stark units holds up to a bounded root of unity. So there's a possible root of unity error, but you have bound on what root of unity error. So we have a formula for these units. So now this is kind of like, this slide is basically like a sales pitch, right? So somehow we want to say that we've provided a p-adic solution to Hilbert's 12th problem. So Hilbert's 12th problem is viewed as asking for the construction of the field f(ab) using analytic functions depending on f. The Brumer-Stark units, together with other explicit and easy to describe elements, and I'll say this precisely later, we prove that they generate the field f(ab). So we prove that the Brumer-Stark units basically give you everything that you want in f(ab) up to some easy things that you can also write down. Now our exact formula expresses the Brumer-Stark units as p-adic integrals of analytic functions depending only on f. So you only need f to begin with to write down these formulas. And you can actually generate them on a computer, and you can spit out elements in these extensions. Therefore, the proof of this conjecture, of these conjectures, these results that I've described, can be viewed as a p-adic solution to Hilbert's 12th problem. Now, the reason that one must take this with a grain of salt is that Hilbert's problem was really stated in terms of complex analytic functions and transformation formula for complex analytic functions, similar to modular functions, which have an important sort of transformation property. And so we're not really addressing the problem that Hilbert directly asked. And so this is a sort of a p-adic version of what Hilbert asked. So that's why one has to be generous in order to say that this is a p-adic solution to Hilbert's 12th problem. Okay, now I want to say in more detail about what these L functions are and what are the Brumer-Stark conjecture and what is the Gross-Stark conjecture. So let me sort of start from scratch there. So I'm going to define first a zeta function. So we know the Riemann zeta function, and we want to generalize this when we're working over these fields f. So associated to my field f is its ring of integers, which I called O. So remember, if a field is Q, then this O is just Z. And for every non-zero ideal, we define its norm to be the size of the quotient ring. So you take the ring and you modify the ideal. It turns out for these rings, any non-zero ideal, the quotient is finite. Okay, and its size we call the norm of A. And excuse me, we define the zeta function of f to be just the sum of 1 over norm of A to the s. So in the case when your field is Q, this ring O is Z, the non-zero ideals are just indexed by the positive integers. The norm of the ideal generated by n is just the number n again. So you just get the sum of 1 over n to the s. So this is just the usual Riemann zeta function when f is Q. And just like for the usual Riemann zeta function, there's a factorization as a product over maximal ideals of 1 over 1 minus norm of p to the minus s. This was the formula discovered by Euler in the case of the Riemann zeta function, and it generalizes very naturally using the theory of unique factorization in these rings to these Dedekind zeta functions. Again, so I mentioned that when f is Q, your zeta function is just the usual Riemann zeta function. For Q adjoin I, we can write down exactly what this is. So for Q adjoin I, all the ideals are principal. So this is generated by m plus ni. What's the norm of the ideal generated by m plus ni? It's just the usual norm of m plus ni. It's m squared plus n squared. So you're summing 1 over m squared plus n squared to the s as m and n range over all non-zero pairs. But of course, you've counted every element every ideal 4 times because there's 4 units in this ring, plus or minus 1 and plus or minus I. So you have to divide by 4. Right? So that's the zeta function of Q adjoint I. Okay. Now, a beautiful formula is the class number formula, analytic class number formula, which was done sort of in the quadratic case by Dirichlet in 1839, and for general number fields by Dedekind in 1894, which is usually expressed in the literature as the residue of this zeta function at s equals 1. But it turns out to have a more clean formulation if you use the functional equation to describe it at s equals 0. So the sum that it described, 1 over norm of a to the s, it only converges for real part of s greater than 1. But it turns out that there's a functional equation satisfied by this function, which allows you to extend its range of definition to the entire complex plane. And once you do that, you can talk about the value at 0. So this is just theory of analytic continuation. The function analytically continues to s equals 0, and you can ask for the value there. And it turns out that it has a 0 over a certain order, and that order has an algebraic meaning. The order of vanishing of this sort of analytic function, complex analytic function, has an algebraic meaning. It's the rank of the unit group of your ring of integers, O. And then if you take the derivative there at s equals 0, that's what's the leading term. If you normalize it in the usual way by dividing out by r factorial, then the value turns out to be something that's easy to remember. It involves 3 fundamental important algebraic invariants of this ring O. So H, this is called the class number of F. This is the size of the Picard group of OF. OF is just O. This is basically the group that I defined before, except it's not the narrow one. It's a quotient of that. So up to a power of 2 is the same as what I wrote earlier. R is what's called the regulator of F. I'll have to define this later because it's more complicated. It has to do with the units, again, in O star. And W is the simplest invariant. It's just the number of roots of unity in N. So it's the torsion size of the torsion subgroup of O star. Okay, so sort of the quantities R and W can be defined together just by saying that this O star, it can be easily shown to be a finely generated abelian group with a cyclic torsion subgroup. So it has the form z to the r cross z mod wz. So that defines sort of R and W.
So the right side doesn't depend on little r?
I mean, little r is an invariant. I mean, I don't know what it means. Like, little r is not something that you choose. It's a specific number. It's the rank of O star, right?
Yes, sorry.
Right. So the order of vanishing of this function at s equals 0 is this particular number, and I'm telling you one value for which is kind of the first non-zero derivative, right? The leading term. But you're right. There are more interesting studies of the other Taylor coefficients of L functions. I don't know about for this zeta function, but in other contexts, in the function field context, for example, people like Wei Zhang have studied the other Taylor coefficients of these L functions. Usually people in number theory usually only study the leading coefficients, but it is a good question of what are the other Taylor coefficients? Do they have an interesting meaning? So that's a good question. So let me just do an example. So about what the regulator is, it's better to give you an example before defining it. So if the field is Q adjoint root 2, then the ring of integers in this case is just Z bracket root 2. So the numbers of the form A plus B root 2 where A and B are integers. And the unit group is generated by 1 plus root 2 and minus 1. So that's isomorphic to Z cross Z mod 2Z. So the R is 1. The W is 2, and it turns out that for this ring, the class number is 1. And what is the regulator? The regulator in this case is just the logarithm of this unit, right? Just the logarithm of this element that generates the free part of the unit group. And so the class number formula then in this case is that there's the order of vanishing is 1, which is the rank R here, which is 1 copy of Z here. And the leading term is negative log 1 plus root 2 divided by 2. Okay. Now, why do we find this formula so interesting as number theorists? Why does this captivate us? So there's a lot of people like to talk about it's relating something analytic to something algebraic. I think it's a little bit of a fake thing because it's kind of soft analysis going into looking at these special values, right? Deep analytic number theory doesn't just ask for the value at one point, but for example, it's why I didn't consider the Riemann hypothesis an example of one of these special values conjectures. It's kind of a different style of question. It's asking about the location of all the zeros, not just the value at some specific point that you care about. The reason that I think this is really interesting is not that it's a connection between analytic and algebraic, it's that it's a connection between local and global. That is, the zeta function can be made by taking really simple local invariants. That is, for each maximal ideal of your ring O, I'm asking for one number, which is the size of the field that you get when you mod out by that ideal, right? That's called the norm of P. So I take these integers, norm of P, whatever they may be, and I package them together into some function that you define following Euler, the Euler product, 1 over 1 minus norm of P to the minus S. So this is a locally defined function. It just has information about the sizes of the residue fields at every maximal ideal. And then when you go back and you look at the special value at certain points of this function that you obtain by analytic continuation, you obtain a really interesting and deep global invariance of the ring O, right? So this knows about the whole ring O, not just all of these little quotients, O mod P, the class number, the regulator, and the number of roots of unity. So that's what's kind of fascinating, is that somehow this local data knows this global data. So it's a local to global principle in number theory. So now let me talk about a generalization of these zeta functions called L functions. So for this, I need to give you some piece of data that's undefined, which is called the Artin map. So there's a certain function, which I won't define, which to each maximal ideal of P that doesn't contain N, there's a certain associated element called the Frobenius that's an element of the Galois group of Fn over F, this group that sort of is told to us what it is by class field theory. Okay, and Artin's generalization of the zeta function is for each character of the group G, you can define what's called the Artin L function, L of chi S, which is just like the Euler product, 1 over 1 minus norm of P to the minus S, except you add a sort of a scaling factor, a dampening factor to the norm of P to the minus S term, which is just the value of the character applied to this Frobenius. Okay, and because this is only defined for the Frobenius is only defined for P's that don't contain N, you take this product over all P's that don't contain N. These are the maximal ideals of your ring that don't contain the integer N. So for example, if chi was the trivial character, if this were just 1, then you would get back the zeta function, except you'd be missing some of the Euler factors. You'd be missing the P's that contain N. That would be the only difference. Okay, and with respect to this definition, Stark made an amazing conjecture that says that we can somehow try to generalize this class number formula by talking about what's the leading term at S equals 0 of this Artin L function that generalizes the zeta function. Okay, so the zeta function was for the trivial character, and now Artin is putting in this character, and Stark is saying, well, if you look at S equals 0 and look at the leading term, it should again be something related to units. Remember before we had the log of the unit, that's exactly what Stark says should appear. So this is Stark's conjecture, which is that there exists a unit in the upstairs field, Fn, a special unit in the field that we don't know how to generate, Fn, that we really wish we knew how to generate, such that for every character of your group, that the leading term at S equals 0, so the derivative, I mean, it's not necessarily the leading term, but I'll just say the derivative at S equals 0 of L of chi 0 is -1 over U, -1 over W, again, this number of roots of unity appearing in the denominator, times basically the log of a unit, except you have to involve the character chi somehow. And the way you do that is now U doesn't live in F, it lives in the upstairs field. So it has a bunch of conjugates. And then you scale the log of each of the conjugates by exactly the character chi. And so you take the twisted sum of the log of the absolute values of the units and you get the L function. So this is, from a representation theoretic point of view, exactly the type of analog that you'd expect when you try to make the Dedekind class number formula into an equivariant statement for the group. So this is kind of a very natural type of statement actually to make, even though it was very surprising to the experts from what I understand when I've heard Stark talk about this, that such a statement should be true. He found it computationally and then was bold enough to conjecture that it should be true in general. So there's just some fine print here that hopefully you can't read, which is that for this statement to be correct, there's some assumptions that need to be made here. And one of them is at the top, just to ensure that all these L functions have that all these L functions are at least 0 at 0, and that so then it makes sense to start talking about the derivative. Is that if f lands in R, then fn does too. And there's also some technical assumptions about the number of places ramified, and let me just leave that in the fine print. That's the basic form of the conjecture, is that if you just look at the class number formula and make it an equivariant statement, then that statement should hold for these Art and L functions. And the reason this is quite a bit deeper is that this is talking about units existing in an extension of F in these fields Fn rather than just in F. Okay. So now Stark's formula can be manipulated to calculate the absolute value of U under each embedding of F into the Fn into the complex numbers. And so a natural question, this is something that actually I got fascinated with as an undergraduate, is can one refine this and propose a formula for U itself? And so I got interested in this because I was trying to do computations in a cubic case that hadn't been done before. And I got frustrated because I only had a formula for the absolute value of U, and I couldn't figure out how am I supposed to find U if I only know its absolute value. If I give you a complex number and tell you it's complex and its absolute value, how are you going to find the number? So I kind of proposed this as a question in my senior thesis, as to can one propose a formula for U itself? Now, there's actually been a lot of work in this direction. I'm not going to take credit for that, but I just want to point out some more beautiful work of Charlois and Darmon, and also by Wren and Czech, to give precise conjectures for these units themselves rather than just their absolute values. And the reason that I find this such an important question is because the presence of absolute value prevents you from saying you can really solve Hilbert's 12th problem using this conjecture even, because if you had a formula for U, you could say, no, I've got this element that lives in this extension. And maybe you can show that all of these elements together generate all of the Fn's. But if you only have a formula for absolute value, you can't really make that claim. So proving these conjectures of Charles Darmon or Wren and Czech, I think, is a really fantastically important open problem. And because I have no idea on how to prove those conjectures, these Archimedean conjectures, I've kind of worked in the p-adic setting where everything is much more tractable. So now I want to move to the case where these complex absolute values are replaced by valuations at primes, which are just integers and much easier to deal with than logarithms of square roots and those sort of fancy kind of numbers that come out of Stark's original conjecture, which unfortunately seem to be well beyond our understanding at this point. So let me state it. And so there's a prime P here, a Gothic P, that plays an important role. Unfortunately, to make things really precise, I have to take an auxiliary prime Q, which is really not as important, but it's sort of to make a precisely correct statement, I need to include it. And then I fix a maximal ideal Gothic capital P that lives above P. What this means is that this ideal contains this one. That's what we use the word above, just for containment here. And here is the Brumer-Stark conjecture, which is again has the same flavor. It's that there exists a unit upstairs. It's no longer a unit anymore. It's a P unit. That means it could have non-zero valuations at the primes above P. But it has absolute value 1 under each complex embedding of F, and it satisfies a very similar relationship with respect to the L function. So the L function of chi at 0, and there's no derivative anymore. It's just the actual L function. Ignore this factor for a moment. Again, it's now saying it's a twisted sum, again, twisted by the character chi. And instead of a log of an absolute value, we just have a valuation here. This is just an integer. The valuation at the prime capital P of the conjugate of u. So it's exactly the same statement as before, as you replaced a derivative with the value and replaced a logarithm with the valuation. Now, again, I need to make this a plausible conjecture. So on the right side, this is an integer. It's an algebraic integer. It lives in one of these rings O that I described before. This L of chi 0 doesn't always. It needs to be scaled somewhat. And it turns out that Deligne and Rivet proved that if you scale by a factor of the form 1 minus chi of q times norm of q, then it lives in O. And therefore, it's sensible to ask that they could be equal if you scale by some sort of simple factor of this form. So that's the technicality I wanted to mention. It's there just to make the conjecture plausible. Now, of course, you want your unit it's now going to depend on q, excuse me, now that you've scaled by this factor. And so that unit should then satisfy some property with respect to q, which is basically that unit is then 1 modulo q. Okay. So that becomes a reasonable conjecture. And again, realize that if you take Stark's statement and kind of replace the Archimedean prime with this finite prime, you get exactly this statement. It can actually be restated this way. And at the same time, if you take Brumer's conjectures about the annihilation of class groups by Stickelberger elements, then again, it can also be shown to be equivalent to this. So this is kind of a combining of the two conjectures of Brumer and Stark. So here's some pictures. Here's Stickelberger, whose results on valuations of Gauss sums I discussed in my lecture yesterday, and whose work motivated Brumer to make these kinds of conjectures that Stickelberger elements annihilate class groups. Stark, and today I'm presenting sort of the other perspective of L functions. And so, yesterday I talked a lot about Stickelberger and Brumer's work, and today I've talked a lot about Stark's work. And Tate kind of brought this all together in the beautiful formulation that I gave in the previous slide. Okay, so the theorem that I mentioned, I can now state it precisely. I stated it kind of vaguely earlier, which is that there exists an element. So remember, there's supposed to exist an element in in OF bracket 1 over P star. And what we can show, there's an element in that group tensored with Z bracket 1/2 that satisfies all the conditions of the Brumer-Stark conjecture. And we can say that there's a higher rank version of the Brumer-Stark conjecture due to Rubin and Popescu, and I guess just this part is just due to Rubin. And we obtain this result as well after tensoring with Z bracket 1/2, right? And Popescu made a refinement that maybe if I have time, we'll discuss later. This 1/2 is annoying, and I don't think I'll have time to say much about it later, but it's work in progress of myself with my collaborator Mahesh Kakde, and together with two of my postdocs, Jesse Silliman and Julia Wang, where we want to kind of remove this Z bracket 1/2 and get it unconditional. And we have sort of partial progress toward this. So we can do this when the 2-CELO subgroup of the Galois group of your extension is cyclic, and then we have a bound. So from that, you can then bootstrap if it's a any finite abelian group is a product of cyclic groups. So if the 2-CELO subgroup is not cyclic, but it's a product of say K groups, we can sort of think we lose a factor of 2 each time you get another factor. So we can get a bound of 2 to the K minus 1 that you would need to make this statement true. Okay. But we're trying to erase that and get it unconditionally. All right. So now let me kind of rephrase our work, get it into the language of Brumer with class groups and annihilation of class groups, because that's how our work works. So there's a unique element, which is called the Stickelberger element. I defined this yesterday. Such in the integral grouping. So it's really important. This is the theorem of Deligne, Rivet, and Kasunoga, is that it's an element in the integral group ring, such that if I project it under every character of the group G, then I get exactly the L function, or L of chi inverse is the usual normalization, with this normalization factor of Deligne and Rivet that I mentioned earlier. So the fact that there exists something in C bracket G is just because C bracket G breaks up into a product over, indexed by these characters. That's automatic. But the fact that the element that you obtain when you interpolate these values actually lives in Z bracket G is a deep theorem. So this generalized results of Klingon, Siegel, and Shintani that shows that the element lives in Q bracket G, and these authors prove that it lives in Z bracket G. So that's on the analytic side. On the algebraic side, we're going to replace the discussion of the units with a class group. So we define a sort of generalized class group which is the group of fractional ideals of your ring of integers O divided by the subgroup generated by principal elements generated by 1 modulo this auxiliary prime Q. This has the structure of a G module, because given any such ideal, you act by the Galois group and you get another ideal. So this should be OH here, by the way, not OF. This is H is my notation for FN. So, and the Brumer-Stark conjecture basically states that the Stickelberger element annihilates the class group, okay? Because if you take your ideal, your Gothic capital P, and saying that theta annihilates it, if you then take a generator, right? So if it annihilates it, then it's trivial in the class group, which means it's generated by some U. And so now you have your U. If you look at what properties that U has to satisfy, given by how it was constructed, you'll unwind it and see that its valuations are related to L functions, just as the Brumer-Stark conjecture asked. So this is kind of a reformulation of the Brumer-Stark conjecture that I stated earlier about the existence of these units, is to say that theta annihilates this class group. And so you can do this locally prime by prime. So you could try to prove that theta annihilates the class group. So this should here, to be precise, this should be the class group tensored with ZP. It then becomes a ZP bracket G module. And then you can ask for theta to annihilate that class group. And if you do that prime by prime, then you've proven it for the full result. So the key point here is we can only do this for P not equal to 2. Okay. Now there's a stronger refinement of this, which I again mentioned yesterday, which is that for all odd primes, you actually have that theta lies in the fitting ideal of the dual of the class group. So again, fitting ideal I defined yesterday, and I won't have time to do it today, but it's a generalization of an annihilator. It's like a submodule, it's an ideal contained in the annihilator. So these are both sort of ideals of ZP bracket G that you can associate to a module, and it's a finer invariant. It's a sub-ideal. Is there a word for that? An ideal contained inside another ideal. It's and sorry, what happened? Lost my place here. Oh, okay. And right, so what we actually prove is that conjecture of Kurihara, that theta lives in the fitting ideal of the dual of the class group. So I want to end the talk with a discussion of method of proof. Of course, I can't really give details, but I discussed Ribot's method a little bit yesterday. I want to do it, take a zoomed out version and say, okay, this is a fundamental technique in algebraic number theory. So let me just say, like, what is the big picture of how it works? So you're trying to make a connection between two things that originally seem to live in different worlds. So one is this analytic object, the L functions, and the other is this algebraic object, the class groups. How do you make a connection between the two? So the L function is connected to Eisenstein series. So these are certain modular forms that have an explicit sort of Fourier expansion. And the constant terms in the Fourier expansion turn out to be exactly the L functions that you're interested in. So this is kind of a sign that there's something very interesting going on between the modular world and in the setting of L functions that you're interested in, is that the L functions give you one tiny little piece of information about your Eisenstein series, namely one of its infinitely many Fourier coefficients. Okay. Now, the Fourier coefficient that it tells you about is the constant term. Now, the constant term being non-zero is exactly the obstruction of a modular form to being what's called a Cusp form. So the Cusp forms within the world of modular forms play a very important role. And one of the roles that they play, so example, like the most famous Cusp form is the delta function, right? Ramanujan's delta. And the reason that Cusp forms are so important is that related to Cusp forms, we have irreducible Galois representation. So now we're making the link from something that feels analytic to something that feels algebraic. Okay, a Galois representation is a representation of an important group, the group that we're interested in, GF, right? So here's where we've made the bridge from something sort of analytic to algebraic. Somehow the L function is showing up through this process. Now you have something algebraic, you can massage it to get to what you want, which is the class group. So before you go from Galois representations, before you jump to the class group, you produce from the Galois representation a Galois cohomology class. And you can do this precisely because the Galois representation that you're using came from a Cusp form that bore some relationship to an Eisenstein series. So in general, you won't necessarily get a Galois cohomology class coming out of this picture. But because you pass through Eisenstein series on your way through the circle, you end up with a Galois cohomology class. And a Galois cohomology class can be used using Kummer theory to relate to class groups. Now, I realize that for the non-number theorists, a lot of the objects that I've discussed here are probably not necessarily very familiar. But I just wanted to say these are kind of buzzwords that one sees, and this is kind of the way that one passes between these, establishes a connection between these two things whose connection originally is mysterious. And it was Ribet's, amazing idea. Gross described it to me as a thunderbolt that shook the community, that you could go from here to there by passing through this route. And I should sort of give a hat tip. I did on the slide to Barry Mazur. I stole this diagram from a beautiful paper he wrote in celebration of Ribet's 60th birthday back in, I think, 2008. All right.
So apparently also Sayre has something to do with this.
This idea? Yeah. I think, no one ever works in a vacuum, right? So I think Sayre and Mazur and Ribet were thinking about, these ideas.
Sayre was functioning a little bit as the supervisor of Ribet in a certain way.
Yeah.
Informal way.
Okay, so I'm basically going to end with the discussion. This is very technical, so this is probably going to only appeal to the experts, but to now say specifically what are the types of modular forms that we're dealing with. So we deal with what are called group ring valued modular forms. So there's the Hilbert modular forms over F with weight K and Fourier coefficients in ZP bracket G, such that for an application of every character chi of G, you get a form of Nebin type chi. I give a slightly different version of the definition yesterday, but it's equivalent to what I've written here. But the point is that there are Eisenstein series whose constant terms are exactly the element that you care about, the Stickelberger element theta. So that's the reason we care about this. This is the element that you care about is showing up here. And that's why it was important to work with these kind of group ring valued modular forms. So something like this had been considered by Wilds earlier, but Mahesh and I kind of reawakened the interest in the study of these group ring valued modular forms toward the study of the Brumer-Stark conjecture, with the observation that the theta that you care about shows up exactly in the constant terms. Okay, and now we construct a Cusp form, which looks very complicated, but the intuition is just drawn from the very first definition of a Cusp form that anyone sees, right? So how do you define the Ramanujan delta function? Actually, I'm asking, so someone tell me, how do you define the Ramanujan delta function? Take product of Eisenstein's, right? So you take products of Eisenstein series and you subtract them, right? You have E4. The only Eisenstein series and modular forms you know how to write down originally are Eisenstein series. So the first two are E4 and E6. And so you do the silliest thing you could possibly do is put them in the same weight. You take E4 cubed, weight 12, E6 squared, weight 12, and you subtract them with some coefficients in front to cancel out the constant terms. And then you get a Cusp form, meaning the constant term is now 0. So that's what we want to do. You want to take your Eisenstein series that has theta as the constant term, okay? And you want to subtract off some other modular form, say that has constant term 1, and multiply it by theta, and then say, okay, I've canceled the constant term, so it's a Cusp, so it's got to be a Cusp form. Okay, now to get a modular form whose constant term is 1, we need to pass to high weight. So that's called, so it's weight hk plus 1. It's not weight 1 anymore. And therefore, we need to make sense of the difference. We need to multiply this by something and weight k. So you want to know that there exists a vk that doesn't change anything modulo high power of p. So you want vk to be congruent to 1 modulo high power of p, and you want hk to have constant term 1, and you also want vk to have constant term 1, so it doesn't change the constant term of this one. Okay, and then if you do all that, then f is congruent to E1 mod theta, because mod theta, this goes away, and mod theta, the vk goes away. Then you have a congruence between a Cusp form and an Eisenstein series. And I should say that the construction of this vk and hk were done by my postdoc Jesse Silliman, generalizing results of Hida and Chai. Okay, now this gives you a function that's constant term is 0 at infinity, but to be a Cusp form, it needs to have constant term 0 at all cusp, and that's quite a bit more delicate. That's why I say in the last line, this can be modified to yield an actual Cusp form that satisfies f is congruent to E1. So now you have a constant term wow, really running slow on time. Let me do this quickly. A modular form that is congruent to an Eisenstein series, you look at its Galois representation, and from that you produce a cohomology class. So I'm just kind of whirling through this cycle of in Ribot's method. And the splitting field of that Galois cohomology class is an extension of your field H, whose Galois group is naturally a quotient of this class group. So that's a study of some local properties. And the fact that F is congruent to an Eisenstein series means that the Galois representation is reducible. I think these two sentences are reversed. I mean, because it's reducible, you get a cohomology class, and the cohomology class splits through an extension whose Galois group is a quotient of the class group. I apologize. These two sentences are reversed. Now, the fact that the congruence is modulo this theta implies that the fitting ideal of the class group is contained in theta, and an analytic argument that I alluded to yesterday shows that this equality is actually, this inclusion is actually an equality. Okay, so
is it the fitting ideal of the dual of the ideal class group?
You're just predicting my fine print. I think
I'm
this
sorry.
fine print, there's the fine print for you, Christian. Remark, this is only for n equals 1, the unramified case. For n greater than or equal to 1, a more complicated module shows up, which is the Ritter-Weiss module that's endowed with a surjective map to the dual of the class group. So then you only get inclusion of the fitting ideal of the dual. So yeah, and so as written here, this slide is correct, but only because I was assuming n equals 1 without telling you that until I got to the end. Not imagining that anybody could possibly recognize that that would be an error in the general case. So that was very impressive. Okay, so I want to end with the discussion of the exact formula for units. I know I'm out of time. So our conjectural exact formula is given by a p-adic integral. So suppose p is generated by the rational prime p for simplicity, then the formula has the shape that u is the power of p times an integral in the sense of Darmon, a multiplicative integral of the function x with respect to a certain measure defined using the Eisenstein cocycle. This Eisenstein cocycle can be defined through a variety of techniques, such as Shintani's method, the topological polylogarithm as studied by Balance and Kings and Levin, Czech's method. So there are literally a dozen, names I could put here, people that have studied the Eisenstein cocycle, and I apologize for not listing them all. But once you have this conjectural formula, I mean that we've kind of proven that up to a root of unity, you can actually put it into a computer. So I had two of my students, Yijia Liu and Max Fleischer, who programmed this, and it's available on the internet, their code and their results. They have tables of thousands of examples of sort of real quadratic fields and abelian extensions of them generated by computing these integrals. So you compute not just u, but all of its conjugates p-adically, and then you compute the elementary symmetric polynomials of these. Then you get actual elements of you ask the computer, okay, it's going to be a plus b root d over 2, where a and b are integers. What integers does this look like? And it's very easy for the computer to tell you, if you do it to 100 p-adic digits and you get 9, then you know that you're right. And sure enough, when you write this polynomial down and you write down its splitting field, it's exactly the an unramified extension of cyclic unramified extension of degree 4, which is exactly the structure of the narrow class group of this field. And so here's a bigger example, which is a degree 6 polynomial. The numbers are still bigger, but they're still very small compared to 5 to the 100th or whatever it is that we did the precision to. Okay, so this is, and I'm really over time now. Let me just say, this is the theorem that I mentioned, earlier, that we get the, that we get the maximal abelian extension as long as you take all the Brumer-Stark units and some square roots. So now that we have the exact p-adic formula for them, we're giving you a p-adic formula for elements that basically generate this field. Okay, and I'll just mention two ideas that go into this. So an integral version of the Brumer-Stark of the Gross-Stark conjecture that I alluded to earlier, that was proven with Darmon and Pollock and Kakde and Ventullo. There's an integral version that we actually proved due to Gross and Popescu, And there's a relationship between that integral formula and my p-adic integral formula that I had proven earlier when I was a postdoc here at the CRM. And finally, a new technique that we used in the second paper that isn't in the first one is the Taylor-Wiles method of inducing sort of auxiliary primes. So you have to do some horizontal Iwasawa theory. And I'm way over time, so I will stop.
Are there any questions or comments for Samit, both in the local audience and the remote one? If anyone wants to ask a question? Yes, Paul?
Just 1 second.
Oh, wait.
Thank you. I don't know any number theory, but you mentioned.
But now you do.
Now I do. You mentioned analytic functions. Are these analytic functions that you're interested in meromorphic in the whole plane, or is there something special about their domain of definition?
Ooh, that's a really good question. So I mean, are you talking about our work or the prior work, the sort of the classical work?
The general quest.
Yeah, that I don't know. I don't know if it's specified that precisely in Hilbert's question about what the domain would have to be, right? So for the complex imaginary case, we're looking at analytic functions or meromorphic functions on the complex upper half plane. So a very standard way to produce the abelian extensions is to use what are called elliptic units, which are meromorphic functions. They're analytic on the upper half plane, but if you looked at the compactification, they have poles maybe at the cusp, the points that you have to add. They're called modular units, and you can look at their special values, and they generate most of the abelian extensions of quadratic imaginary field. So, so that's the sort of one type of example. Now, if you go into these more exotic type p-adic constructions that we're doing, so Henri and Jan Vonk have a very nice perspective on this, where they look at rigid meromorphic cocycles. So what those are first of all, you look at rigid meromorphic functions on the p-adic upper half plane. Okay, and they have two kinds of papers. They look at the rigid meromorphic ones and the rigid analytic ones. So both show up, and really the thing that's most analogous to the CM theory is the study of rigid meromorphic functions on the p-adic upper half plane. But an important difference I want to make is you don't look at special values of functions. There's kind of a shift in dimension, which is you look at special values of cocycles. That is, you can think of, I mean, this is maybe a little bit loose. You can think of a function on H mod gamma. This is like what shows up in modular functions as a class. You can think of like sort of a function on this. You can think of this as a class in H0 of gamma and functions from H to C, right? It's just a gamma invariant function. And so what they realize is that when you go to say real quadratic field or field of maybe higher rank, this is still conjectural, but you want to increase the cohomology you're looking at. So they'll look at H1 of gamma and functions on the p-adic upper half plane into the p-adic complex. So they'll look at something like that, and they look at special values to take a special value of a cocycles to pair it with a homology class. And so the work that we've done can be reinterpreted in that language.
I think we still have time for one short question. I just got a text from your cab driver.
Okay.
So we don't want to.
Yeah.
Any other questions or comments further from?
So, Samit, congratulations on the results. I mean, these are fantastic results. My students, my postdocs, and I have been reading with great pleasure the papers. One very brief comment for the young people in the audience. So, we don't know what to say at this point about Hilbert's 12th problem when the base field F is not a totally real number.
Oh, yeah.
So please think about that. I mean, there is a Stark conjecture there, which is very precise due to Rubin. There is a gross type conjecture there. And we know that if we solve these conjectures, then Hilbert's 12th problem will be solved. So there is a lot of work to be done by the young people in the audience.
Oh yeah, field is very much open. I mean, I want to say even more than that. Our work very narrow. I mean, like, I don't know how to go just like one step beyond what we've done. So even for totally real fields, Christian, you could look at other types of characters of different signature where they're not totally odd characters like what we look at. And then you have to deal with an Archimedean contribution and we have no idea what to do.
No,
so
absolutely.
So there's a ton of work to be done in basically any setting that goes slightly beyond, what we've done. So.
So you managed to describe the maximal abelian. Thank you. You managed to describe the maximal abelian extension for such fields.
Yes.
And more than that, like the ring class fields there. Now, such a field has other natural structures. For example, its group of units, its ring of integers. Can you at this point use those to?
Certainly at this point I can't, and I'm not even sure whether it would be possible. I mean, like I said, our problem, like our work is very good at doing exactly what it's done and probably
We'll be there in 2 minutes.
not very good for going even just a little bit beyond. So yeah, understanding the Galois module, the ring of integers of this field is probably, I think it'd be hard to do just from knowledge of the Brumer-Stark conjecture. I know Christian has something to say about that, but my personal knowledge is very limited to exactly, I mean, it seems very hard to say. That's why I say you have to be very generous to say solve Hilbert's problem, because you like to answer other questions about these fields now that you've constructed them. And I don't know how to answer any deep questions about the fields that we didn't know how to answer before beyond the ones that we actually answered. So there's a lot of work to be done, as Christian alluded to. Yeah.
And there's also a cab to be caught. So
okay,
I want to thank Samit again for his wonderful and stimulating lecture.
Okay, thank you very much.